Hey, we are now starting chapter 4. So we're really going to start moving along now in terms of new material. Um, and this is super exciting. So we are still going to be looking at axial loading. So we're only looking at that internal normal force. We are still not looking at shear or torsion or bending moments. It's still purely axial deformations. And so the first thing I want to do is just a quick equation review. What do we know? We have that average stress of P over A, where P is that internal normal. It's acting through the centroid. Our area is the cross-sectional area. So like if we were slicing a piece of bread, it would be that piece of bread that we could lay on our table. And that force is a normal force. It's either acting in tension or in compression, but it's acting straight through the centroid, okay, through the centroid. We also have a relationship now between that stress that we've applied, the material properties, when we're in the elastic region, that is modulus of elasticity, and strain. Strain is our deformation. And when we look at strain, it's change in length over original length, where we have length final minus length initial divided by length initial. So we have to make sure that we're keeping up with, if length final is shorter, keeping up with our algebra correctly so that we get a negative strain. If we are in compression, that is a negative stress. If we have a negative stress, when we have E, we're going to have a negative strain. We are getting shorter in that longitudinal direction. We also have Poisson's ratio, which is the relationship between longitudinal strain, okay, that's the direction that I'm applying the force, the axial force, and lateral strain. That is the cross-sectional. It's not in the direction that we're applying the force. So the diameter of a column, as we smush it, okay, it's longitudinally getting shorter, but that diameter is going to get bigger, okay? And so we have Poisson's ratio equals negative lateral. That's just the dimension going along for the ride, okay? Versus over longitudinal. That's the direction of the applied force, okay? So what I need to keep in mind is longitudinal is in the direction of the applied load. Okay, so if I can calculate that using my stress and my E and my strain, then I can go back and I can calculate my new cross-sectional properties. So my original, if we're in tension, we're getting longer. We have a positive delta, we have a positive strain. And so I have my original cross-section, okay, before loading. After loading, you can see we've gotten longer in our bar, and consequently our cross-section has gotten smaller. And that's where, once we get that lateral strain, well, what is strain? It is just change in length over length. It is length final minus length initial over length initial. So when I'm looking at that lateral strain, I can look at a diameter. I can look at a height and a base. If we have a square, if we had a triangle, it would be the edges of the triangle. Okay, so it doesn't matter. Lateral is the direction that we aren't applying the force. It's just going along for the ride. Longitudinal, I always think is the long axis. It's the direction we're applying that axial load. Okay, so there's our strain. So this is, gosh, what is this? This is like chapter 1, chapter 2, and chapter 3 all on one slide. Okay, that's pretty cool. So we're going to talk about, we've been talking about this average normal stress of P over A, and we just assume that every tiny molecule all along that cross section is experiencing the same stress. But we know that that's really not true, okay? We really know that where we have an applied load or where we are fixed, we're actually going to have some distortions. And it's not truly average in those points, but that's okay, okay? So the stress directly under the applied load is going to be larger than the rest of that specimen, the rest of that beam, the rest of that column, okay? But we just kind of assume this average P over A. And what we're going to find is that the regions where we have the very high stress, where we're applying the load, it's a very, very small region compared to the rest of that column, okay? It's actually whatever the width is, that width, if it's a 15-inch wide, even if it's 20 feet tall, 15-inch wide, 15 inches down is where we have the distortion in that area, and then it goes back to the average of P over A. So it's actually a very small area. And you can kind of see as we're cutting down from where we've applied that loads, that we do have a very, very large area right here. I mean, it looks large, but it's just really right here at the top. Okay. And we're going to have a much higher stress right there where we're pushing down on something than we are 2 feet down. Okay. But as we slowly move away from the top, we're coming closer and closer and closer to just that average normal stress. And again, that distance down is the width of whatever we're looking at. Okay, so those peak stresses can be several times larger, but they diminish very, very quickly. So when, again, we look at this, we could look at a different type of loading. So the first type of loading was right there kind of in the center. This is kind of offset, symmetric on the sides. It's going to be the same behavior. Once I go one width down, so here's the width. Once I go one width down, it's back to just the average P over A. Right underneath where I'm applying the loads, it is a much, much greater stress, okay? But it very, very quickly goes back to that average. And so I just want to remind you, we are still only looking at axial forces. We are looking at that internal normal, okay? We have not begun to add any other forces on this. These are truly two force members, okay? Two force members, axial, compression or tension. So when we have normal force and we have zero shear, zero moment, that was chapter 1. Remember, we did all that P over A. Chapter 2 is strain. Chapter 3 is stress strain. Chapter 4, voila, this is our new equation, which we've already kind of talked about. If I know stress is P over A, and I know that strain is delta over L naught, my original length, then I can actually just combine those into the equation that we got in chapter 3 and rewrite this as P over A equals E delta over L naught. And then I can rewrite this equation so that it's just in terms of delta, because many times we are actually trying to find a change in length. Okay, we're actually trying to find a change in length. So we've just written our stress equals E times strain. We've just rearranged those variables. Delta equals PL over AE. For this equation, because we're not integrating, okay, we're not looking at a different sized area that's changing or a different material or an axial load that's changing. This is just E is constant. You know, it's a steel bar. It's got a uniform cross section. It's not variable. It's not like an ice cream cone, maybe where, you know, where it's like a larger area and then it comes down to a smaller area. It has a constant internal force. It's just loaded at both ends. 5 kips, 5 kips. So internal is going to be 5 kips in tension. And super important, we are in the elastic region because E, remember, it's the slope of the elastic region, the stress-strain relationship. So we have to remember to always, always be checking. Now, if we have a compound system where we have several different axial pieces making up a system, then we can look at summing. We can look at summing PL over AE, or you may see F force, or you may see N normal force. It's just that axial load, L over AE. And so that's where chapter 1 is very important, where you cut and you draw the free body diagrams and you're able to draw a normal force diagram, much like a shear or moment diagram or torque diagram, but it's the normal force. So I can now see I'm in tension for parts 1 and 3. That means my delta is going to be positive because I have a positive internal normal. I'm in compression for segment 2, which is negative, so that's going to be a negative stress, a negative P over A. My delta will be negative. So it's super important to keep up with positive beam notation, okay, positive beam notation, because it's going to dictate whether it's a positive delta or a negative delta. Okay, so super, super important to keep up with positive. Always assume intention, and then do your statics, your equilibrium, to find out if it's truly in tension or if it's in compression. Okay, So again, you have to make sure that you are cutting your axial members appropriately. Um, like I always do, what do I always use? I always am taking post-it notes and I'm like covering everything above or covering everything below. You cannot just pull out segment 2 right here and look at the 2 blue arrows and say, oh, that's my force in the middle. No, it's either everything below. So if I start over here in the figure all the way on the right, I am essentially covering up everything above the middle of CD. Okay, I want to find out what the force is from in that segment C to D. So I'm going to cut it so I can find that internal. I either have to look at the very bottom piece or I have to look at that whole top piece. And if I look at the top, which is kind of like very light right there, it's like I covered it up, but I can still kind of see it's there. I would have to find the reactions. Okay, I would have to find the reactions. So if you have a free end, which we call like a cake problem, okay, it's got a free end, start at the free end and then you don't have to find reactions. Okay, and then keeping up with, am I in compression or tension? You just sum up those deltas so that you can get an overall change in length. Okay, what about having a varying force or a variable cross section? So it's still going to have that PL over AE look, except now when we look at those differential elements as we're going, we're going to have to do some integration. So we could have a force that's a function of the length. We could have a cross-sectional area that varies with length. Again, think of an ice cream cone. Okay, when you look at an ice cream cone, that cross-sectional area varies with the length. We could also have a varying axial force. So you can do integration. But first, you always have to check yielding. If you want to use delta equals PL over AE, it has to be in the elastic region. So the first thing you should always just do from here on out is every time you calculate an internal force, you need to calculate what is the internal stress. And you need to find out, is that stress in the elastic region? Is it below sigma y? Or is it above? Because then it's no longer in the elastic region where we can use delta equals PL over AE. So what if I find the internal stress of an A36 bar is 60 KSI? So we should know that an A36 bar, that yield stress is 36 KSI. Okay, that it's 36 KSI. That's where we leave the elastic region. So if I have 60 KSI, it is greater than 36 KSI. It has yielded, okay? This is only, we can use stress equals E times strain in the elastic region. So if we find that it is indeed an internal stress of 60 KSI, okay, but let me, I guess, back up. If we look at the strains down here on the bottom, remember the bottom numbers are with the elastic kind of curve. They're very, very tiny. In fact, they're a magnitude of 100 smaller than the strains that we would see if we look at the overall chart. So remember the upper chart has these larger strains because that's actually a much bigger part of our graph. And you can see right here on the left as we go up a very, very, very tiny line kind of going up. That's the elastic region. You could not use these upper values to calculate anything in the elastic region. So we stretch out the elastic in part of this initial yielding and we use much, much smaller values, okay? So if I were at 36 KSI or less, I'm going to have super small strains, super, super small deformation, okay? That's usually where I'm going to want to design. If I'm at 60, and I'm using these tops, you can see that that number you're going to get for 60 is much, much bigger than any value that you would get in the elastic region. So 60 KSI. Here, if I wanted to just look at what is stress equals E times strain, and I used that modulus of elasticity because I'm assuming it's elastic, I would get a strain of 0.00207, or I could call that 2069 microstrain. Okay, so very, very tiny. but it's actually larger than that. It's actually not in the elastic region. So I can go to a stress strain curve, okay? I can go to a stress strain curve like this, and I can find where my stress equals to 60, and I can come over to the overall stress strain diagram at 60, and then I can draw down and I can guesstimate, okay, I see a 0.1 and a 0.2. 0.15 has to be this little click right here in the middle. So this might be 0.14, maybe 0.145. And I can guess, so that's the strain. I can just pull a strain off the chart. Strain equals 0.145. That is so much bigger than the 0.00207 I would get if I used the elastic region, okay? So I'm finding that here is my strain, 0.145. That is enormous compared to 0.00207. So being outside of elastic, but using the elastic properties, you're going to get really, really wrong values. You're going to look at like 0 change in length versus 6 inches of change in length. Like visual, you can see the changes. It's no longer a small strain. So from here on out, you have to check. And what about when we're in torsion and we're looking at shear? Yes, there's a yield for shear. I'm always going to have to check to make sure I'm in that elastic region, because that's where our stress equations that we use are valid. I'll do some examples now. Oh, there you can see it's much, much larger.